Hi everyone, my name is Pia Englyst and I work at the Danish Meteorological Institute. Today I will present a study where we have used satellite-derived surface temperatures to benchmark climate models and reanalyses in the Arctic. As you are probably all aware of, climate change is most pronounced in the Arctic, with a warming rate much higher than the rest of the world. But how much more has the Arctic actually warmed? Despite much attention, there has actually been limited consensus on the magnitude of Arctic amplification over time. In 2016, most research showed that the Arctic was warming about twice as fast as the global average. In the sixth assessment report by IPCC from 2021, it was stated that it's very likely that the Arctic has warmed more than twice the global rate over the past 50 years. Later the same year, the Arctic Council affirms that the Arctic is warming about 3 times the global rate. The latest research indicates that it's actually closer to 4 times the global average and makes it clear that the previous studies have been seriously underestimating the magnitude of Arctic amplification. Even today, there are large uncertainties in existing Arctic surface temperature estimates, and the magnitude of Arctic warming and amplification varies among the different observational and model datasets. So why is it so challenging to provide accurate Arctic surface temperature estimates? Well, there are more reasons for that, but here I have identified 2 key challenges which both complicate an accurate and absolute estimation of Arctic surface temperatures. The first one is related to the large reduction in sea ice cover. As you can see from the map here, the Arctic is generally experiencing more and more open water days, up to a month more with the days with open water in some regions. And this means that there are some areas which were previously mapped as sea ice that are now shifted towards open ocean. And why is this challenging? Well, traditionally the satellite-observed sea and sea ice surface temperatures have been derived and analyzed individually. But it's pretty hard to estimate the temperature trend of an area which keep changing size and shape. Moreover, most of the existing in situ-based datasets are based on a mix of satellite-observed sea surface temperatures over open ocean and in situ measured near surface air temperature, typically measured about 2 meters over sea ice. And this combination can also complicate the surface temperature calculations, since the changing sea ice cover leads to shifts between the 2 variables, and artifacts of the varying techniques may thereby be introduced into the data record. And that is clearly undesirable in context of climate monitoring. The second challenge is related to the very sparse in situ network in the Arctic, which limits the observations available to observational-based dataset and atmospheric reanalyses, which currently don't use any satellite-observed ice surface temperature over sea ice, which means that they are actually based on only a very limited number of observations in this very sensitive region. Both of these challenges cause large deviations and uncertainties in the Arctic surface temperature estimates. Therefore, there is a need for more consistent surface temperature estimates of the Arctic to better benchmark climate models and to improve our overall understanding, characterization, and monitoring of the Arctic warming and amplification. At DMI, we have recently developed the first daily gap-free combined sea and sea ice surface temperature climate data record of the Arctic using satellite observations. I will not go into much detail here, but both the data and the documentation can be found in the link and the reference here at the bottom of the slide. As you can see in the first map, this dataset covers both the sea ice, the marginal ice zone, and open ocean. It is based on clear sky observations of sea surface temperature and ice surface temperature from infrared satellite sensors. As you can see in the second map, there are gaps due to clouds. And these gaps are filled using a method called optimal interpolation to produce daily gap-free fields of temperature, surface temperature, and corresponding uncertainties. The combination of sea and sea ice surface temperature means that this dataset brings a new possibility of consistent climate monitoring of the Arctic Ocean since 1982, despite the temporal varying sea ice cover. This graph shows the surface temperature trend in terms of monthly anomalies, and it reveals a total surface temperature increase of 4.5 degrees over this period. As you can see from the map, it has not warmed the same everywhere. There is a peak warming in the northeastern Barents Sea of up to around 10 degrees. This dataset provides new spatially detailed information on the surface temperatures over sea ice. And as already mentioned, the existing observational datasets, reanalyses, and gap-free climate data records, they currently don't take into account this ice surface temperature information from satellite observations. Therefore, to supplement the sparse in situ network in the Arctic, we have investigated the potential of using the satellite-observed ice surface temperatures to derive near-surface air temperatures. This is done using an empirical model which was developed in the Horizon 2020 project called EUSTES some years ago. The empirical model was trained and validated against in situ measurements. As you can see from the first map, the red ones being the in situ observations used for training, and the blue ones the in situ observations used for validation. And in EUSTES, we developed separate models over sea ice and the Greenland ice sheet. And the animation here shows an example of the satellite-derived 2-meter air temperatures for all days in January 2008 compared to in situ observations, which are marked as the circles. We have applied the same model to derive gap-free 2-meter air temperatures over Arctic sea ice from the satellite-derived ice surface temperatures for the entire climate data record. The graphs here illustrate an example from one buoy where the in situ measured near-surface air temperatures in black is compared to the ice surface temperatures from satellite in the top, and the derived 2-meter air temperatures from satellite observations in the bottom. And you can see that after converting our ice surface temperatures into 2-meter air temperatures, we have a much better agreement with the in situ measured air temperatures. The table summarizes the validation results for 3 different types of in situ measurements, and if we use the same in situ observations to validate ERA5, we find that ERA5 is too warm compared to the observations. And this is a problem because ERA5 is often used in climate assessment and as benchmark for climate models. And this can lead to wrong conclusions, such as assuming that the climate models are too cold. This has actually been the case, and it's known as the long-standing cold bias in the Arctic. The long-standing cold biases in the Arctic area are seen across all CMIP phases, as shown in the maps here, where ERA5 has been used as benchmark. The biases, or mean differences as we would rather like to call it, are in the range of 2 degrees, and they are largest during winter of up to more than 4 degrees. So far, model evaluations have mostly been based on global reanalysis data, but our satellite-derived surface temperature products provide a new possibility for benchmarking climate models and reanalysis in the Arctic. This is illustrated in this slide here, where our satellite-derived 2-meter air temperature dataset is used as reference to evaluate both ERA5 and CMIP6. This comparison reveals another story. Here, the CMIP6 actually performs significantly better than ERA5 in the Arctic Ocean, with annual mean differences of less than 1 degree, while ERA5 has mean differences of several degrees, and again, the largest differences are observed during winter. Both ERA5 and CMIP6 are too cold in the marginal ice zone, with the largest discrepancy for CMIP6, and this is likely due to an overestimation of the sea ice cover in many of the CMIP6 models. This information from the satellite observations can therefore be used to guide future developments in both climate models but also reanalyses, and it also provides new insights into the Arctic warming and amplification. This graph here illustrates the temperature trend in our satellite-derived 2-meter air temperatures for the central sea ice with sea ice concentrations above 70%. And how does the Arctic warming in our dataset actually agree with the observed trends for ERA5 and CMIP6? These two graphs here shows the deviations from the satellite-derived 2-meter air temperatures for ERA5 in red and CMIP6 in blue. It is evident again that CMIP6 shows a mean difference around 0 throughout the entire period, while ERA5 consistently provides too warm temperatures compared to the satellite-derived surface temperatures. It is also evident that both ERA5 and CMIP6 underestimate the warming in the central Arctic Ocean with about 0.2 degrees per decade compared to the satellite-derived 2-meter temperatures. So including or simply learning from the satellite-derived temperature estimates might enable us to better represent the Arctic warming. If we replace the Arctic 2-meter temperatures in ERA5 with the satellite-observed 2-meter temperatures for the entire sea ice cover, the Arctic amplification estimate increases from 3.8 to 4.2. So these initial results indicate that the Arctic warming may still be underestimated in ERA5, and they demonstrate the value of having spatially detailed satellite-derived surface temperatures of the Arctic sea ice. So to summarize, we have presented the first gap-free combined sea and sea ice surface temperature climate data record of the Arctic, which enables consistent climate monitoring of the Arctic Ocean, where the sea ice cover is declining rapidly. The dataset reveals that the combined sea and sea ice surface temperature has warmed with 4.5 degrees on average, and with a peak warming in the northeastern Barents Sea of about 10 degrees. To supplement the limited in situ observations, we have derived a new 2-meter air temperature dataset over sea ice based on the satellite-observed ice surface temperatures. The spatially detailed information provides a new possibility for benchmarking climate models and reanalysis in the Arctic. Using information from the satellite-derived 2-meter air temperatures may improve the representation of the Arctic warming and amplification, and I've just shown that in our initial results actually indicate that the Arctic amplification may still be underestimated. If you want to read more about this work, it has recently been published in this Nature here by Tian. Thank you very much for listening.